So there's several things to discuss in section 3. The first thing is multinomial distribution, which is mentioned on page 299. And you may or may not have heard of multinomial coefficients, but basically the multinomial theorem extends the binomial theorem. Choosing comes up in places other than the binomial theorem, but everyone runs into this in high school where you've got to expand something like this. Maybe you didn't actually have this problem, but you might want to expand something at least squared or cubed, right? And the question is, what is the coefficient of, well, really any term, but let's say x cubed y squared. And so how do you do this from scratch? Well, most of you know how to do this, but let's just go through it. As a reminder, since we'll do multinomials next, we've got 5 parentheses, each with x plus y in it. We need to pick 3 of them. We need to pick an x from 3 of them and a y from 2 of them. So that is 5, choose 3. And the remaining 2 can be y's. And we know that this is 5 factorial over 3 factorial times 2 factorial. Another way to think of this is arrange x, 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 y, y. So there's 5 letters, 5 factorial ways to arrange that, but you don't actually want the x's to be able to be permuted, so we divide that out. There's 3 factorial ways to permute the x's, divide that out. 2 factorial ways to permute the y's, divide that out. And as we said, that's the same as 5 choose 2, because you could have picked the 2 parentheses from which to take a y, and then the remaining ones are x's. In fact, you could just write this as 5 choose 3 and 2. You choose 3 of one thing, 2 of the other. And this leads us into multinomials. Binomial means 2 things, right? So 2 terms, x and y. Multinomial means there could be more. Let's just do x, y, z to the power of 5. And now we want to find the coefficient of x squared, y squared, z. For example, z to the 1. Okay, well, same principle, right? You have 2 x's, 2 y's, and a z. You want to rearrange them, so 5 factorial, but you don't want to allow the x's to be rearranged, so divide out by 2 factorial. Don't want to allow the y's to be rearranged. Divide out by another 2 factorial. The z is kind of trivial, but we'll keep that 1 factorial there. And then the notation for this is 5 multi-choose 2, 2, 1. Which corresponds to this notation that we just introduced there. So that's what multi-choose means. You can have as many numbers down here as you want. The numbers down here must add up to the top number. So it's splitting up that many into different groups, and then how many ways are there to rearrange that. Other thing to go over in this section is stars and bars. This is a classic technique in combinatorics. And it answers this question: how many ways to put 6 identical balls into 3 boxes, boxes A, B, and C. So the boxes are not identical. Balls are identical. Some boxes can be empty. Arguably, all combinatorics is about putting balls into boxes. That is what I spend my life studying. Okay, so how can we represent this as... It looked like we were having good success with permuting words, so we're going to try to do that here. Words don't have to be represented by letters. In fact, here they'll be represented by symbols. So the balls will be represented by stars. And then you're going to have 6 stars for 6 balls. And then what we're going to do is we're going to add 2 dividers, or bars. And then what that does, let's say they go there and there. That means that everything before the first divider is in box A, everything between the 2 dividers is in box B, and everything after the last divider is in box C. So you've got 2 balls in box A, 3 balls in box B, 1 ball in box C. And the problem becomes permute these letters. There's 6 stars, 3, 4, 5, 6, and 2 bars. And you can permute them any way you want. The bars can go at the end, the bars can be next to each other because boxes can be empty. So like, for example, if this were the permutation, all 6 balls go in box A, no balls in box B, and no balls in box C. That works. Okay, so that's that technique. And then we know how to count the number of those permutations. Here, so in our A shuffle, which is what they're talking about in this section, we have A piles of cards. So that corresponds to, there's N stars for the cards, total of N cards in all A piles. And then we want to add A minus 1 bars. Right here there were 3 boxes, we only added 2 bars. So here there's A piles. We're going to add A minus 1 bars. And then what they're saying in this section is that R minus 1 bars are accounted for by the rising sequences. Every time you have a new rising sequence, you know where a bar has to go. And there's A minus 1 total bars, so if we subtract that off, there's A minus R bars left that you can put wherever you want. That's what they're talking about in that section. Okay, another thing, page 303, corollary 1, there's a typo. There's no comma at the end on the last line of that corollary. So what it should read is A equals A1 times A2 all the way to AK. They put a comma after A1. There shouldn't be a comma there. Okay, corollary 2, another example of not understanding everything in a paper and having it be okay. I'm a combinatorialist, not a probability theorist, so I read this a little bit less closely. I haven't read that Rogers-Pittman paper or result. I don't know what completeness means in this context, and I'm not, in general, sure how to verify if something is a Markov chain, what conditions they need, and that seems to be what they're doing here. I'm not going to worry about it. I can still read the proof and verify some of the details, and then move on and know what results follow from it. Some of you are very interested in probability theory, so you might want to look into some of these things. I did not. The rest of the section, don't worry too much about page 304 and the top of 305. You can skim all that, but basically you need at least Math 504, which is graduate abstract algebra, to fully understand all this, and I've taken that and I still don't understand everything in it. So yeah, this is a lot of abstract algebra. It's not a big deal. You don't need it to fully understand the rest of the paper. What happens if you get a section like that, though, is you may not understand 100% of everything that follows, and that's okay. So start back reading a little bit more carefully in the section where it says Coxeter groups. That's the second section on page 305. So read all of it. You won't understand some of the sentences unless you do have some abstract algebra background, which is certainly not required for this course. You won't understand some sentences. You will understand some other sentences. So you get something out of that section. It's okay if you don't understand every word. This is how reading a math paper goes. If you wanted to then pursue some of the results and extend their work, then you might have to go back and read other papers or books and figure those things out. But just reading through the paper the first time, not a big deal.